Space is not a void, and time is not a river. What you and I experience as the solid, unshakable foundation of our lives, the three dimensions we move through, the steady tick-tock that carries us from past to future, may be the most profound illusion in the cosmos. Beneath the familiar surface of our reality lies a maddening paradox. The greatest theories of physics, the twin pillars of relativity and quantum mechanics, describe a universe that is flexible, probabilistic, and granular. A universe where the stage itself can bend, ripple, and may not even exist at the most fundamental level. Our senses tell us one story, but the mathematics tells another. This isn't just a philosophical puzzle. It is the central, unsolved mystery of science. And it leads to an unnerving question. If the very fabric of existence is not what it seems, then what is it? What are we? Tonight, we journey into the heart of this enigma. We will peel back the layers of certainty, from the clockwork cosmos of Newton to the warped, strange reality of Einstein, and finally to the quantum foam where everything we know dissolves into uncertainty. We are on a hunt for the ultimate nature of our universe. Stay with me as we ask the most fundamental question of all. What are space and time? Part 1. The foundation. What is space? What is space? The question feels nonsensical, like asking, what is air made of? Before we knew of molecules. It is simply there. It is the backdrop, the stage. As children, we learn its rules intuitively. Up and down, left and right, forward and back. A three-dimensional grid, a universal platform on which the drama of existence plays out. This conception of space is so deeply embedded in our minds that challenging it feels like challenging the ground beneath our feet. For millennia, this was the accepted view. The great philosophers of ancient Greece gave it shape. Plato saw space as a formless receptacle, a nurse of becoming, a medium that contained everything but had no properties of its own. His student Aristotle took it a step further, arguing that a true empty void was a logical impossibility. Nature, he famously declared, abhors a vacuum. To them, space was defined by what was in it. Without objects, space itself was meaningless. This idea held sway for 2,000 years. But as humanity emerged from the Dark Ages, a new way of thinking was crystallizing. The universe, it turned out, was not governed by the whims of gods or mystical forces, but by laws. Immutable, predictable, physical laws. And these laws could be described not in myths or stories, but in the pure, cold language of mathematics. This was the dawn of modern science, and at its heart was a debate that would define our reality for centuries. It was a debate about the very nature of the stage itself. But before we meet the titans of that debate, our investigation must begin on the water. It begins with a boat. In 1632, the Italian astronomer Galileo Galilei published his masterwork, a book whose title translates to Dialogue Concerning the Two Chief World Systems. Galileo was an old man by this point, in his late 60s, and no stranger to controversy. He had already faced the wrath of the Roman Inquisition for his dangerous assertion that the Earth was not the center of the universe, but instead orbited the sun. To avoid further trouble, he framed his book as a simple dialogue, a conversation exploring different ideas about the cosmos. And buried within this work is a thought experiment of profound importance. Galileo asks us to imagine a sailor, locked below the deck of a ship in a windowless cabin. On a table in the cabin sits a collection of objects: plates, knives, and a bowl containing a single goldfish. Flying around the room are birds, flies, and butterflies. First, imagine the ship is tied up in port, perfectly still. The cabin is a picture of serenity. The goldfish swims happily. The cutlery stays put on the table. The insects and birds flutter about in every direction without preference. Everything is calm. Now, imagine the ship is caught in a violent storm. The cabin heaves and rolls with the waves. Plates are thrown from the table, water spills from the bowl, and the flying creatures are dashed against the walls. The motion is chaotic and violent, and the sailor feels every lurch. But then Galileo imagines a third scenario. The storm has passed. A steady wind fills the sails, and the ship glides across a glassy, Calm sea at a constant speed and in a straight line. Inside the windowless cabin, what does the sailor experience now? Logic might suggest he would feel the motion, the rush of the ship through the water. But Galileo realized this was wrong. Inside the cabin, serenity returns. A dropped plate falls straight to the floor, just as it did in port. The goldfish swims undisturbed. The flies and butterflies once again flutter in random directions. For the sailor, sealed off from the outside world, there is no experiment he could possibly perform, no measurement he could take. That would tell him whether the ship was moving at a constant speed or sitting perfectly still in the harbor. All smooth, uniform motion feels exactly like being at rest. With this simple, elegant thought experiment, Galileo shattered a 2,000-year-old assumption. He concluded that there can be no absolute concept of rest in the universe. Motion is not an absolute state. It is always relative to something else. An observer on the shore would see the ship moving. The sailor on the ship would feel he is still. And neither of them is wrong. With this, the first theory of relativity was born. Think about what this means. Right now, as you sit here, you are on a planet spinning on its axis at over 1,600 kilometers per hour at the equator. That planet is orbiting the sun at 67,000 kilometers per hour. The entire solar system is hurtling around the center of the Milky Way galaxy at a staggering 720,000 kilometers per hour. And our galaxy itself is being pulled toward the Andromeda galaxy at 403,000 kilometers per hour. And yet, like Galileo's sailor on a calm sea, you feel nothing. Your coffee stays in your cup. The air in your room is still. You feel at rest, adrift on a vast cosmic journey millions of kilometers from where you were just an hour ago. Galileo's insight was a monumental step, but it created a paradox. If all motion is relative, how can we measure anything? This question brought two of the 17th century's greatest minds into a bitter conflict. On one side was Isaac Newton. Born in England in 1642, the same year Galileo died, Newton is a figure who needs no introduction. His laws of motion and universal gravitation laid the foundation for classical physics, a system so powerful and predictive that it would dominate science for the next 200 years. For Newton, Galileo's relativity was a problem. To make his laws of motion work, to calculate the gravitational pull between planets, he needed a fixed, reliable backdrop, a universal reference frame. So, Newton declared that space was a universal absolute, a rigid, unchanging, infinite stage on which all motion played out. This absolute space, he argued, existed in its own right, independent of any matter within it. It would be there even in a universe completely devoid of stars, planets, or people. On the other side was his rival Gottfried Leibniz. A German philosopher and mathematician, Leibniz was a leading intellectual of his day, a man who pondered deep metaphysical questions like, why is there something rather than nothing? To Leibniz, the idea of an empty, absolute space made no sense at all. He argued that space was not a container, but rather the sum total of the relationships between objects. Space, he claimed, only has meaning because of the relative locations of things. In a universe with no matter, there are no relationships, and therefore space and time simply cease to exist. They have no role to play. Their feud, which had already been ignited by a bitter dispute over who invented calculus, came to a head over another simple thought experiment. It did not involve a boat, but a bucket. Newton asks us to imagine a bucket of water, hanging from a rope. First, the bucket is at rest. The surface of the water is perfectly flat and level. Now, we begin to spin the bucket. At first, the bucket spins, but the water inside lags behind, its surface remaining flat. But soon, friction catches up. The water begins to spin along with the bucket. And as it does, its surface becomes concave, curving upwards at the edges. Newton then posed a simple but devastating question. What is the water spinning relative to? It can't be spinning relative to the bucket because at the end of the experiment, they are moving together. It can't be spinning relative to the room or the earth because Newton argued that if you performed this experiment in a completely empty universe with nothing else in it, the water would still curve. The acceleration of the spin, Newton claimed, was proof of absolute space. The water feels the spin because it is accelerating with respect to this fixed, invisible, universal stage. Leibniz was not convinced, arguing that the very concept was meaningless, but he died in 1716 with the argument unresolved. In the end, it was Newton's vision that won. His physics was too successful, too predictive to be ignored. For the next 2 centuries, the scientific consensus was that we live in a universe of absolute space and absolute time. As Newton wrote, absolute space in its own nature, without relation to anything external, remains always similar and immovable. Absolute, true, and mathematical time of itself, and from its own nature, flows equally without relation to anything external. And yet, Galileo's ghost lingered. Newton had established an absolute space, but he could not establish an absolute rest. The sailor in the cabin was still a problem. So science settled into an uneasy compromise. Space was the absolute stage, but you could never know for sure if you were truly stationary on it. Relativity still applied to smooth, uniform motion, but that was only for space. Time, everyone agreed, was a different beast entirely. What is time? If space is the stage, then time is the conductor. A universal, unswerving metronome, dragging the entire cosmos forward with a single, unified beat. For Galileo and Newton, a second on Earth was a second on Jupiter was a second in the most distant, unseen corner of the universe. Everyone's clock, everywhere, ticked in perfect, absolute synchronicity. Time had a direction, an implicit arrow pointing from a fixed past towards an unknown future. It was the current in which all events flowed. But what is this current? Does it have properties of its own, or is it defined only by the events that happen within it? To begin answering these questions, we must turn away from the abstract world of physicists and their clocks and rulers, and toward something much more practical. We must turn to the world of heat, horses, and steam engines. The Industrial Revolution of the 18th and 19th centuries presented humanity with a new kind of problem. The traditional engines of civilization, animals like horses and oxen, were simple. You knew that a certain amount of hay and water would guarantee a certain amount of work. But these newfangled steam engines were different. How much work can you really get out of a pile of coal? Is it more efficient to replace a horse with an engine? This was a critical economic question, and out of this very practical conundrum, a new branch of physics was born, thermodynamics, the study of heat and energy. Scientists and engineers wrestled with the problem. A typical engine of the era was shockingly inefficient, wasting up to 97% of the energy it consumed. Heat from the burning coal was used to boil water into steam, but much of that heat simply radiated away into the air. Metal scraped against metal, losing energy as friction and noise. In any real-world machine, this loss of energy as waste heat seemed inevitable. The mathematics of thermodynamics soon revealed why. Perfect efficiency, they found, was a physical impossibility. Energy, they realized, is always lost when it flows from one place to another. The concentrated, useful energy from burning coal must be degraded as it moves through the engine. Some of it does useful work, but a portion of it must always be lost to the surroundings as disordered, low-grade heat. To account for this relentless process of decay and disorder, physicists introduced a new concept. They called it entropy. Entropy is, in essence, a measure of disorder. And it is simple probability that dictates its behavior. The physicist George Gamow described it beautifully. Think of the room you are in now. The air molecules are spread more or less uniformly from wall to wall, floor to ceiling. You never worry that all the air will suddenly collect itself in one corner, leaving you to suffocate. This horrifying event isn't physically impossible. It's just so extraordinarily improbable that the waiting time for it to happen by chance is trillions upon trillions of times longer than the age of the universe. There are vastly more ways for air molecules to be disordered and spread out than there are for them to be ordered in one corner. Disorder is always statistically more likely. The new laws of thermodynamics revealed that this principle applies to everything. The universe as a whole has an inexorable tendency to move from order to disorder. Entropy always increases, not just in steam engines but in planets, stars, and entire galaxies. They are all on a one-way march from an ordered past to a more disordered, decayed future. In 1862, the Scottish physicist Lord Kelvin, for whom the absolute temperature scale is named, followed this idea to its grim, logical conclusion. He wrote, "Although mechanical energy is indestructible, there is a universal tendency to its dissipation. The result would inevitably be a state of universal rest and death, if the universe were finite and left to obey existing laws. This is the concept of the heat death of the universe. A future where all the stars have burned out, all potential energy has been converted into useless waste heat, and the cosmos becomes a dark, cold, and empty place." And so, physicists began to wonder, was this it? Was this the physical basis for the arrow of time? A universe constantly moving towards its own inevitable heat death. A steady march where entropy always increases? One of the great minds to grapple with this question was James Clerk Maxwell. To explore the implications of entropy, he imagined a tiny, intelligent being, a demon. Imagine a box filled with gas at a uniform, warm temperature. The box is divided in two by a wall with a tiny door, controlled by Maxwell's demon. The demon can see every individual gas atom and knows its speed. As the atoms fly about, the demon performs a simple task. Whenever a fast-moving, hot atom approaches the door from the left, he opens it and lets it through to the right side. Whenever a slow-moving, cold atom approaches from the right, he lets it pass to the left. Over time, the demon, without expending any energy himself, has sorted the gas. The right side of the box becomes hot, and the left side becomes cold. He has taken a disordered state, the warm gas, and created a more ordered one, hot and cold separated. He has decreased the entropy inside the box, seemingly breaking the second law of thermodynamics. Maxwell's demon is only a thought experiment, but for over 150 years it has forced physicists to think deeply about what entropy really is. The resolution, many now believe, is not about energy, but about something else: information. To do his sorting, the demon needs to know the speed of each atom. He uses information, and this reveals a profound, and initially bizarre, link between the physical concept of entropy and the abstract concept of information. The link has become stronger and stronger over the past century. Think about a modern computer. As it processes information, it generates a tremendous amount of waste heat. But the physics is more subtle than that. It isn't just the processing of information that generates heat, but the forgetting of information. Imagine a simple logic gate in a computer performing addition. Two electronic signals go in, say, the numbers 2 and 3. One signal comes out, the number 5. But in producing the answer, the inputs are lost. The gate has forgotten them. If you only know the answer is 5, you cannot know for certain what two numbers were added to get it. The calculation is irreversible. And physicists discovered that in the very act of this irreversible forgetting, a tiny, unavoidable amount of energy must be released as waste heat. This is a fundamental limit of physics called the Landauer limit. It is the inescapable cost of erasing a single bit of information. That tiny puff of heat increases the total entropy of the universe. Ultimately, it is this irreversibility, this constant forgetting of information on a microscopic scale, that drives the relentless increase of entropy in the macroscopic world. It is what separates the past from the future. Is it possible, then, that for tomorrow to exist we must be able to forget yesterday? Is the arrow of time itself tied to our inability to remember everything? The foundations have been laid. We have a classical picture of the universe, built by the giants of science. A universe that plays out on Newton's absolute stage of space, but where motion is strangely relative thanks to Galileo. A universe where time is an absolute universal clock, but whose one-way direction is mysteriously governed by the laws of disorder, probability, and the forgetting of information. This was the state of our knowledge at the turn of the 20th century. A powerful, useful model of reality, but one that was groaning under the weight of its own internal contradictions. It was a foundation full of cracks. And a revolution was coming. A new order that would shatter the stage, break the clock, and lead us directly to the bizarre, flexible, and deeply strange nature of our universe. To continue our journey, we must now explore a new kind of space. Part 2. The Investigation. New Space. The universe described by Newton and Galileo was a masterpiece of order and reason, a majestic clockwork machine set in motion on an absolute stage. But as the 19th century drew to a close, cracks began to show in this perfect facade. A ghost in the machine was making itself known. And that ghost was light. The story of how we first tamed light is a story of cosmic patience. In 1676, the Danish astronomer Ole Romer was meticulously timing the orbits of Jupiter's moons. He assumed their celestial dance was as predictable as a pendulum, and he could use their eclipses, the moments they slipped into the planet's shadow, to set the clocks of the world. But his predictions kept failing. Throughout the year, the eclipses would drift, falling behind schedule and then catching up again. Romer realized the problem wasn't with the moons, but with the messenger. The light from Jupiter had to travel to Earth, and as the two planets moved in their orbits, that distance changed. When Earth was farther from Jupiter, the light took longer to arrive. With this data, his contemporary Christian Huygens made the first real calculation of light speed, a stunning 211,000 kilometers per second. Light was finite, but unimaginably fast. For 2 centuries, this was just a number. But then James Clerk Maxwell, the same man who wrestled with the demon of entropy, achieved one of the greatest unifications in the history of science. He took the seemingly separate phenomena of electricity and magnetism and wove them together into a single, elegant set of equations. And buried deep within his mathematics, an incredible truth emerged. Light, he found, was nothing more than a wave of oscillating electric and magnetic fields, propagating through space. And his equations didn't just describe light, they predicted its speed. A speed that matched the measurements almost perfectly. But this triumph created a profound paradox. Maxwell's equations gave a precise speed for light, but they failed to answer a critical question. Relative to what? Galileo's sailor could only measure his speed relative to the shore. A ball thrown on his ship has a speed relative to the ship, and a different speed relative to the shore. You simply add the velocities. This is common sense. But Maxwell's equations had no room for this. They gave one speed, an absolute speed. This was a direct contradiction of Galileo's principle of relativity. It implied that there was, after all, a fixed state of rest in the universe, a universal reference frame against which the speed of light was measured. Physicists gave this reference frame a name: the luminiferous ether, a mysterious, invisible, undetectable substance that filled the entire cosmos, acting as the medium through which light waves traveled, just as sound travels through air. This was the mundane explanation, preserved Newton's stage and Maxwell's equations. The only problem was no one could find it. Experiment after experiment designed to detect the Earth's motion through this ether came up empty. The universe was hiding its tracks. The official story was failing. It took a mind of singular genius to see the truth, not to try and fix the old theories, but to propose a new one, built on a foundation that seemed, at first, like pure insanity. In 1905, a young patent clerk in Bern, Switzerland named Albert Einstein wondered, what if Maxwell's equations were right? What if Galileo's relativity was also right? What if the contradiction wasn't in the physics, but in our most fundamental assumptions about reality? In a bold, revolutionary leap, Einstein declared that the principle of relativity must apply to everything, including electricity and magnetism. On Galileo's ship, he proposed not only would a dropped plate fall the same way, but a beam of light would be measured to have the exact same speed, whether the ship was in port or sailing smoothly on the sea. The speed of light in a vacuum, he stated, is constant for all observers, regardless of their own motion. This simple statement shattered the classical world. If two observers moving at different speeds both measure a beam of light to have the exact same velocity, then something else has to give. Common sense must break. And what broke were the absolute foundations of Newton's universe. The only way for the math to work was if space and time themselves were not absolute. Each observer, Einstein realized, must have their own personal measurement of space and their own personal measurement of time. Your ruler and your clock are not the same as mine. The faster you move, the more your time slows down and the more your space contracts relative to a stationary observer. With his special theory of relativity, Einstein demoted space and time from the rigid, universal stage to flexible, relative players in the drama. The only true absolute was the speed of light. The implications were staggering, and it took other great minds to fully grasp them. In 1908, Einstein's former professor, Hermann Minkowski, realized what Einstein's equations truly meant. He saw that space and time were not just intertwined. They were two sides of the same coin. He proposed merging the three dimensions of space and the one dimension of time into a single four-dimensional entity. He called it spacetime. In a famous lecture, he declared, "Gentlemen, the views of space and time which I wish to lay before you are radical. Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Newton's stage had been completely rebuilt. But Einstein wasn't satisfied. His special theory of relativity was a masterpiece, but it had a glaring omission. Could not account for gravity. Newton's law of gravity depended on the distance between two masses, but special relativity now told us that no two observers could even agree on what that distance was. Worse, Newton's gravity acted instantaneously across the cosmos, a spooky action at a distance that violated Einstein's new universal speed limit, the speed of light. So he went back to the drawing board for another decade of intense, solitary thought. What emerged in 1915 was the general theory of relativity, a solution so profound and beautiful that it shocked the world. Einstein took Minkowski's geometric picture of a unified spacetime and did something audacious. He made it bendy. He proposed that mass and energy don't exist within spacetime. They actively curve and warp the very fabric of spacetime around them. And what we perceive as the force of gravity is nothing more than objects following the straightest possible path through this curved, distorted spacetime. The Earth doesn't orbit the Sun because of a mysterious invisible pull. It orbits the Sun because the Sun's immense mass creates a deep dimple in spacetime, and the Earth is simply rolling along the edge of that valley. With general relativity, gravity as a force ceased to exist. Newton's picture of the universe was now truly dead. Not only were space and time relative, they were dynamic, flexible, and shaped by the contents of the universe itself. The bizarre consequences of this new reality were quickly uncovered. The theory predicted that massive objects should literally bend the path of light, a prediction famously confirmed during a solar eclipse in 1919 that made Einstein a global superstar. It also predicted that time itself runs slower in stronger gravitational fields. A clock at sea level ticks ever so slightly slower than a clock on a mountaintop. This isn't a mechanical error. Time itself is passing at a different rate. In 1971, this was proven directly in a beautifully strange experiment. Physicists bought tickets for a set of hyper-accurate atomic clocks on commercial airliners, sending Mr. Clock on a round-the-world trip. When the flying clocks were reunited with their stationary twin on the ground, their times no longer matched. They were off by a few hundred nanoseconds, almost exactly the amount Einstein's equations predicted. But there were even stranger things lurking in the mathematics. In 1916, just a year after Einstein published his theory, Carl Schwarzschild found a solution to the equations for a perfectly spherical mass. His solution described an object so dense that it would curve spacetime back on itself, creating a region from which nothing, not even light, could escape. He had discovered, on paper, the black hole. And near a black hole, where gravity is immense, the curvature of time becomes extreme. To a distant observer, time near the heart of darkness would appear to tick almost to a halt. And the theory predicted one more spectacular phenomenon. If spacetime can bend, it must also be able to wobble. A massive, accelerating object, like two black holes spiraling into each other, should send out ripples in the fabric of spacetime itself. Einstein himself was unsure if these gravitational waves were real or just a mathematical artifact. It would take a century to prove him right. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a pair of dead stars orbiting each other, and they found the orbits were slowly shrinking, leaking energy into the universe at precisely the rate predicted if they were emitting gravitational waves. Then, in 2015, the LIGO Observatory made the first direct detection. Hearing the faint chirp of two black holes merging over 1 billion light-years away, a ripple that stretched and squeezed the entire planet by less than the width of an atom. Einstein's new space was a dynamic, living entity. Could bend, it could ripple, it could expand. And that last part, discovered in the 1920s, was perhaps the most shocking of all. The universe is not a static stage. The space between galaxies is growing. It's not that galaxies are flying away from us through space. It's that the space itself is being created between them. This cosmic expansion leads to a mind-bending conclusion. A galaxy far enough away from us is receding faster than the speed of light. This doesn't violate relativity's speed limit, because that limit only applies to motion through space. Here, space is simply carrying the galaxy away. This expanding, dynamic spacetime creates deep philosophical problems that haunt physicists to this day. For example, it breaks one of the most fundamental laws of physics, the conservation of energy. In a static universe, the laws of physics are the same yesterday, today, and tomorrow. This symmetry guarantees that energy is conserved. But in an expanding universe, the stage itself is changing. The physics of tomorrow's universe is not identical to today's. As a result, energy is not conserved. As photons of light travel across the expanding cosmos, they are stretched, losing energy. The universe is slowly being robbed of its energy as it grows. It now seems we have our answer. Space is not nothing. It is a physical thing. It can bend, expand, curve, and ripple. It is the very medium of gravity. But there is one final, maddening twist. A final rug to be pulled from beneath us. The great Nobel Prize-winning physicist Steven Weinberg once said that in Einstein's relativity, spacetime is truly nothing. It has no properties of its own. The mathematics just looks like bending and curving. How can this be? We have just built an entire new reality on the concept of a physical, dynamic spacetime. And yet, one of its greatest interpreters tells us it's an illusion. The investigation into space has led us to a deeper, more unsettling paradox. And we have yet to fully confront what this new reality did to its twin. How did the dawn of relativity affect our understanding of seconds, hours, and the very flow of existence? What is the nature of this new time? Part 3. The investigation continued. New time. The future civilization, huddled in their shell around a black hole, knew the secret. They had exploited it for their very survival. They knew that time was not a universal river, but a local stream, could be dammed, diverted, and made to flow at different speeds. Their engineers had bent it to build their empire, and in their final days, they used its sluggish flow near the immense gravity of their home to watch the universe die in fast forward. Time for them was a tool. But for us, it is a mystery that cuts to the very core of what it means to be. With Einstein's revolution, the simple, comforting idea of a universal now was obliterated. If my clock and your clock tick at different rates depending on our motion and gravity, then we can never agree on a single, simultaneous moment across the cosmos. This isn't just a measurement problem. It's a fundamental feature of reality, and it leads to a chilling, philosophical headache known as the block universe. Imagine the life of a single particle, a single electron. We can trace its journey through the 4 dimensions of spacetime as a continuous line, from its past to its future. Physicists call this a world line. Every particle in your body is tracing its own world line. Before you were born, these lines were scattered across the globe. For the brief flicker of your existence, they are bundled together into the intricate knot that is you. And when you are gone, they will disperse once more. You are a temporary pattern in the fabric of eternity. This seems poetic, but the headache comes when you ask, when is now? In Newton's universe, you could slice through all the world lines at a single instant of absolute time and declare, this is the present. But relativity forbids this. There is no universal slice. My now is different from the now of someone in the Andromeda galaxy, and neither is more correct. The devastating implication is that if the past, present, and future are not absolute, then they must all be equally real. The entire history of the universe, every event from the Big Bang to the final heat death, is already out there, laid out in the four-dimensional block of spacetime. In this view, the cosmos doesn't unfold from moment to moment. It simply is. Our consciousness traces its path along its predefined world line, experiencing the illusion of a flowing present, like a spotlight moving along a film strip that has already been printed. Concepts we hold dear, like free will, seem to evaporate. Our future is just as fixed as our past. But this cannot be right. Our experience screams otherwise. We remember the past, but the future is a closed door. They feel fundamentally different. An egg can be scrambled but not unscrambled. A cup can fall and shatter, but the pieces will never reassemble themselves and leap back onto the table. There is a clear, undeniable arrow of time. So where does it come from, if not from the fundamental laws of physics? This is where the mystery deepens. Consider two electrons hurtling towards each other. They repel through the electromagnetic force, their paths curving away. If you were to film this interaction and play it backwards, it would look perfectly normal. Two electrons would approach each other and curve away. The fundamental laws of electromagnetism, gravity, and the strong nuclear force are time-symmetric. They do not care which way time flows. This is a profound disconnect. The macroscopic world we inhabit, which is just the collective behavior of trillions of atoms governed by these time-symmetric laws, has a powerful unidirectional arrow of time. How does this arrow emerge from a multitude of interactions that are themselves ignorant of time's direction? The answer, it seems, can only be found by looking at the universe as a whole. The block universe of relativity is an idealized model. Our real universe had a beginning. 14 billion years ago, it was born in an incredibly hot, dense, and strangely smooth state. This initial smoothness is the key. While a smooth gas in a box represents high entropy or disorder, a smooth distribution of matter in the early universe, under the influence of gravity, represents a state of incredibly low entropy. It was a universe wound up like a perfect clock, full of potential energy. Gravity could then pull the smooth matter together, forming stars and galaxies, processing ordered potential energy into the disordered waste heat of starlight. The universe's entropy has been increasing ever since. Our arrow of time, the difference between past and future, seems to be nothing more than a cosmological artifact, a memory of the universe's very special birth. Just how special was it? The physicist Sir Roger Penrose calculated the odds of our universe beginning in such a low-entropy state by chance. The number is 1 in 10 to the power of 10 to the power of 123. A number so fantastically, absurdly large that to write it out would require more zeros than there are atoms in the entire observable universe. Our existence, our perception of time's flow, is balanced on a statistical improbability of cosmic proportions. And yet, even within this framework, the bendy, flexible nature of Einstein's spacetime allows for even stranger possibilities. If mass can curve spacetime, could it be curved so much that it loops back on itself? On June 10, 1944, a Dutch volunteer pilot named Willem Jacob van Stockum was flying a Halifax bomber over Nazi-occupied France when it was struck by flak and crashed, killing the entire crew. His name is now lost to history, but before the war, van Stockum was a brilliant physicist. And in 1937, he was the first person to discover a scientific basis for time travel. He was exploring a peculiar solution to Einstein's field equations, one that described a hypothetical, infinitely long, rotating cylinder of dust. As he mapped out the world lines of particles in this universe, he found something shocking. The intense rotation would drag spacetime along with it so violently that time and space would become indistinct. He found world lines that weren't lines at all, but loops, closed time-like curves, that allowed a particle to travel into its own past. This was no science fiction fantasy. It was a direct mathematical consequence of general relativity. His work was largely forgotten until after the war, when it was rediscovered by the eccentric genius Kurt Gödel, one of the greatest logicians in history. In 1949, as a 70th birthday present for his friend Albert Einstein, Gödel presented his own solution for a rotating universe, one that was also filled with paths to the past. Einstein was, in his own words, deeply disturbed. If his own theory allowed for such paradoxes, what did it mean about the nature of reality? Our universe, as far as we can tell, is not rotating like girdles. But other relativistic structures, like wormholes or the churning spacetime inside a spinning black hole, also theoretically permit these time-like loops. Time travel remains a stubborn, theoretical possibility, written into the very DNA of Einstein's theory. The stage we play on is not just flexible. It may be folded, twisted, and riddled with shortcuts to yesterday. We have pushed relativity to its absolute limits, and it has given us a universe that is stranger than we could have ever imagined. But relativity is only half the story. To complete our investigation, we must now turn to the other great pillar of 20th century physics. We must journey from the cosmic scale of gravity to the subatomic world, into the realm of quantum mechanics. Quantum spacetime. A university student attending a lecture on general relativity in the morning and one on quantum mechanics in the afternoon might be forgiven for thinking his professors are fools who have not spoken to each other for a century. The two theories are the twin triumphs of modern physics, yet they paint two completely incompatible pictures of reality. General relativity describes a smooth, deterministic universe of curved spacetime. Quantum mechanics describes a fuzzy, probabilistic world of discrete energy packets, where particles can be in multiple places at once. For nearly a century, the quest to unite them, to find a theory of quantum gravity, has been the holy grail of physics. The first step was taken by a man Niels Bohr called the strangest man to ever visit his institute. Paul Adrien Maurice Dirac was a man of few words. His colleagues at Cambridge jokingly defined a new unit, a Dirac, as 1 word per hour. But his mind raced. He was bothered that the new quantum mechanics was built on the old, outdated stage of Newton's absolute space and time. He knew it had to be rebuilt to incorporate Einstein's special relativity. In 1928, after years of struggle, he found it, a relativistic quantum equation. It was an immediate, spectacular success. When applied to the electron, the equation naturally explained properties like its intrinsic spin without any extra assumptions. But it also had a strange quirk. Just as the square root of 4 can be +2 or -2, Dirac's equation had two solutions. One described the familiar, negatively charged electron. The other, he eventually realized, predicted a new particle, an anti-electron, with the same mass but a positive charge. He had predicted the existence of antimatter, a direct consequence of uniting the quantum world with spacetime. Dirac's equation was the birth of quantum field theory, the language we now use to describe all fundamental particles and forces. But it was built on the special theory of relativity, a flat, uncurved spacetime. When physicists tried to incorporate the curving, bending, rippling spacetime of general relativity, the mathematics broke down completely. The infinities became uncontrollable. The two pillars of physics refused to merge. This failure has forced physicists to ask a much deeper question. Maybe the problem isn't the theories, but our underlying assumption. Maybe space and time aren't the fundamental stage we think they are. This has led to radical new ideas. In string theory, the fundamental constituents of the universe are not point particles but tiny, vibrating strings in 10 or 11 dimensions. Spacetime, as we know it, is just one part of this complex, multidimensional structure. In a rival theory, loop quantum gravity, space and time are themselves quantum phenomena. If you could zoom in to the tiniest possible scale, the Planck scale, you would find that spacetime is not smooth. It's a granular, chunky network, a subatomic mesh. Our smooth, continuous reality is an illusion that emerges from the collective behavior of these atoms of spacetime. But what are these strings or loops made of? The theories don't say. They just are. This leads to the final, most profound, and perhaps most unsettling possibility. Perhaps Newton was wrong and his rival Leibniz was right all along. Perhaps space and time do not exist as independent entities. What if they are not fundamental at all but are emergent? We are familiar with emergent phenomena. Temperature is one. A single water molecule doesn't have a temperature. Temperature is a collective property, the average kinetic energy of a vast number of molecules. What we feel as heat emerges from this microscopic chaos. What if space and time are the same? What if, at the most fundamental level of reality, there is no where and no when? What if there are only fundamental bits of information and a complex network of relationships and interactions between them? This idea, known as the holographic principle, suggests that our entire three-dimensional universe could be a projection of information stored on a two-dimensional surface at its boundary. In this view, space-time is like a screen, and the pixels that make it up are the true reality. There is no space between the pixels, no time that flows from one to the next. There are only their relationships. And somehow, from this abstract relational network, the illusion of our vast, smooth, three-dimensional stage emerges. This may feel deeply uncomfortable. Where are you in this relational universe? But perhaps it is no more strange than the fact that your consciousness, your sense of self, emerges from the electrochemical chatter of a collection of unthinking atoms in your brain. We have learned to live with the illusion of our own solid being. Perhaps we must now learn to live with the illusion of the stage on which we play out our existence. Part 4. The conclusion. We began our journey with a simple question. What are space and time? We started on the solid ground of Isaac Newton, in a universe that was a grand, predictable clockwork machine, playing out on an absolute and unchanging stage. It was a comforting reality, one that aligned with our everyday senses. But our investigation has systematically dismantled that reality, piece by piece, leaving us adrift in a cosmos far stranger and more mysterious than we ever imagined. We have traveled a long road. We saw Galileo's sailor prove that there is no absolute rest, that all smooth motion is relative. We watched the bitter feud between Newton and Leibniz, a debate over whether space was a real container or just an abstract web of relationships, a question that, centuries later, remains unanswered. We saw how the practical problem of steam engines led to the concept of entropy, and how the inexorable increase of disorder, probability, and the act of forgetting may be the only things that give time its arrow. Then came the revolution. Einstein shattered the clock and broke the stage. He took the absolutes of space and time and made them flexible, personal, and intertwined. He revealed a universe where gravity is not a force but the curvature of a unified spacetime, a dynamic fabric that can bend, ripple, and expand. This new reality gave us black holes where time grinds to a halt, gravitational waves that carry the echoes of cosmic collisions, and even the theoretical possibility of looping back into our own past. Finally, we descended into the quantum realm, the final frontier. There, we found that the two great pillars of modern physics refuse to unite, that the smooth fabric of Einstein's spacetime dissolves into a fuzzy, probabilistic foam. We were forced to confront the most radical idea of all, that space and time may not be fundamental, that they might be an emergent illusion, a grand projection arising from a deeper, information-based reality where concepts like location and duration have no meaning. We are left with a profound dichotomy. On one hand, we have our direct experience, the solidity of the floor beneath our feet, the undeniable passage of time, carrying us from a remembered past to an unknown future. This is the reality our brains evolved to navigate, the user interface for our existence. On the other hand, we have the mathematics of our best physical theories. They describe a universe where the stage is an illusion, where time's flow is a consequence of cosmic initial conditions of absurd improbability, and where the fundamental reality may be a timeless, spaceless network of pure information. This is the central conflict, the lingering question that lies at the heart of modern physics. Is our universe a story that is being written, unfolding moment by moment from an open future? Or is it a book that has already been written, where past, present, and future are laid out in their entirety, and we are merely turning the pages? The search for an answer, for a theory of everything that will finally unite gravity and the quantum world, is the great challenge of our time. It is a quest that may lead to sudden, shocking clarity. We may one day grasp an idea so simple and so beautiful that we will wonder how we could have been so blind. Or, we may find that with every new discovery, space and time just become more elusive, their true nature forever receding beyond our grasp. We must face the humbling possibility that some mysteries may be too profound for the human mind to solve, that the fundamental truth of what space and time are could remain forever beyond our horizon. And so we return, Finally, to the twilight of the cosmos, to that last civilization huddled in the darkness. They had mastered space. They had bent time, but they could not defeat them. They were characters in a story, playing their part on a stage whose true nature they, like us, could never fully comprehend. In the end, all that was left was their relationship to the universe, and then that too faded into nothing. Our journey ends here, not with an answer, but with a choice. A choice in how we view our own existence. We can live our lives on the surface, accepting the illusion of a solid stage and a steady clock. Or we can carry with us the unsettling knowledge that we are adrift in a cosmic enigma, that the very foundations of our reality are a mystery. It is the choice to remain content with the map or to forever seek the nature of the territory itself. The ultimate question is not just what space and time are. The ultimate question is, what are we, these fleeting patterns of consciousness, who have the audacity to ask?